Okay, welcome everybody to this week's session of the Beyond Spacetime seminar. We have as visitor and the speaker today Elena Castellani, who's an associate professor at the University of Florence in the Department of Philosophy. She did her laurea in theoretical physics at the University of Florence and then her PhD in philosophy at the University of Milan. She had many fellowships then that sustained her in the years after that in many various places, too numerous really to list all of them. She works, some of which you will see in a minute, on history, philosophy, physics generally, on the philosophy of space and time, on structure, on dualities, on emergence, reductions, string theory, symmetry. Did I not mention that? Yes, symmetry, very, very centrally, of course. And I'm very, very happy to have her here today. So please, Elena Castellani on Duality and Emergence, the case of Weakstrong duality.
Thank you, Chris, for the invitation. I'm happy to be here. Also because Switzerland is something near on my heart. I was born in Switzerland, so it's nice to be here again. And so let me start. Is it working? Yes. Duality versus emergence. Yeah, I will consider the comparison between these two notions in a special framework, that is special frameworks. That is the framework of quantum field theory on the one side and string theory. But here, in fact, I will speak just about quantum field theory. But with the Weakstrong duality I'm considering is applied now in string theory. It's an essential ingredient of string theory. So this is the frameworks we consider, and the motivation for investigating this relationship in such frameworks is the following one, that we notice that the notions of duality and emergence seem to be closely related in these frameworks. First of all, because dualities seem to lead to emergent features, but at the same time, they have contrasting features. We have this strange situation. That is, in particular, duality is a form of equivalence between two theoretical descriptions, and so then the objects, phenomena that are described. So it's a symmetrical relation, while emergence, implying novelty, seems to be an asymmetrical relation, typically. So these are the standard view on these two notions. So why? I don't understand why it does this strange thing each time that, okay. It's not a problem, huh? I was just wondering.
It's just a particular way, I guess.
It's nothing, not a problem, huh?
No.
Just leave it. So the issue, the motivating issue for investigating this comparison in such frameworks is how to put together these two apparently contrasting features. So it's a puzzle, and like all puzzle, it starts its motivation for investigation. So let's start with emergence. I will not spend much time on that notion since you all know very well the whole discussion and you have heard talks before on emergence with detail. Let me just take as starting point for emergence the classic reference for it, that is the two papers that Jeremy Battlefield wrote in 2011 with the title Less is Different and then subtitles. And we can use his definition for emergence in this context. That is, emergence characterizes properties of behavior which are novel and robust relative to some appropriate comparison class, where novel is defined by, is characterized by Jeremy in this way, not definable from the comparison class, and robust the same for various choices or assumptions about the comparable class. This will be enough for our scope. And the two typical cases that are considered in the literature that are discussed of emergence in this sense is when a system is a composite. So its properties and behavior are novel and robust compared to those of its component system, and typically microscopic system composing a macroscopic one. And when the system is a limit, when we have limiting relation among theories, like the case of thermodynamics and statistical mechanics. So these are the typical cases described. The case that I will consider today is something like a mixture of these two aspects. We will have the composite characteristic and the limit characteristic. So it puts together these two situations, but in a different way. Okay, this is all I have to say about emergence for the moment. And what kind of issues we have about this notion? Which sort of relation is emergence? And in the literature, this is discussed by comparing emergence with other notions, typically the notion of dependence, of reduction, supervenience, and then we have different characterizations, synchronic versus diachronic emergence. Transformational is a new category introduced by the Sartner. Epistemological versus ontological. It depends on the items that are related to this way. And what we consider here is emergence versus duality. Of course, you all know the work, the position of Jeremy Butterfield about the compatibility between emergence and dependence and reduction. This was the scope of his papers. In a sense, we are doing the same here. We are showing that they are compatible, notwithstanding the contrasting feature. Can you hear me well?
Yeah.
Okay. So which kind of dualities are we considering here? I have said which kind of frameworks, and we are in these frameworks. We are considering two cases. I'm saying we because this is in fact a joint work with Sebastian de Haro. You have heard his talk on emergence and gauge gravity duality. So this is the part of Sebastian, and I will focus on the second part, emergence and Weakstrong duality. So these are the two case studies that we have considered in comparing emergence with duality. There are many other kinds of dualities, but we are focusing on these two cases. Just to remind what the conclusion of Sebastian de Haro, he considered the gauge gravity duality, that is the equivalence relation between a quantum gravity theory defined in a volume and the quantum field theory, gauge theory is defined on the surface. And in that case, his conclusion on the relation between emergence and duality was the following, was that the novel features could emerge not through the duality but through the coarse-graining approximation. The coarse-graining, where the coarse-graining takes place on each side of the duality, so that the emergent behavior takes place on each side, and the duality maps one emergent behavior to the other. So it's like to replace the original duality with a series of duals, each of them valid at the correspondent level of coarse graining. So it's like having a family of theories related pairwise by the duality at each level of the coarse grain. So the emergence takes place independently of the duality, so it would seem that there is no correlation, but it's not exactly so. As Sebastian showed you, when the duality depends on an external parameter, then the way in which the coarse graining is obtained depends on that parameters. And so the duality says in which way the approximation and the emergence feature obtains. So in this sense, they are correlated. This was the part of described by Sebastian. He has made various papers on it appearing, and so he has developed this part in great details. Okay, so just to define the first part of this work. Now let's focus on this second case of duality with Weakstrong duality, which is a basic ingredient in field and string theory, especially since the 90s. What is Weakstrong duality? So in very general terms, we can say that it's an equivalence map between two theoretical descriptions, or theories if you want, of the same physics, such that the weak coupling region of the first theory is met to the strong coupling region of the second theory, and vice versa. So you can see it's a very useful tool for non-perturbative calculation. When you have strong coupling and you can't use the perturbative approach, then you just go to the dual theory, which is a weak coupling theory. Where you have weak coupling, you can do the calculation using the perturbative approach, and then you can just transpose to the other theory what you obtain. So this was one of the main reasons of interest in this kind of dualities, because when you have strong coupling, you have difficulties in doing calculations. So in this very general definition, one needs to clarify, first of all, in what this equivalence exactly consists, and what is intended by the same physics, two theoretical description of the same physics. But I will be quite quick. I will give examples so it will become more clear. So let's stay still in general, and I will use here a characterization by the theoretical physicist Ashoke Sen, who is one of the leading physicists in this area, applying dualities to string theories and in the 90s and later on. So let's see how to characterize in general terms in a more precise way. Duality, so this kind of duality is a statement of equivalence between two, also more apparently different quantum theories, where apparently different means this, that these quantum theories, when you take the classical limits, then they have classical limits which are genuinely different. So you can also, you have this actually identical quantum theories which have different classical limits. We'll see better in which sense this obtains. And the equivalence, the statement of equivalence is done in this term that there is a unitary transformation relating the Hilbert space of the two theories, under which all correlation functions in one theory are mapped exactly to the corresponding correlation functions in the other theory. Sebastian has given also a very precise definition of duality in terms of isomorphism, so I'm not going into more detail here. This kind of duality, what is of special interest for the relationship with emergence is this feature, this apparently puzzling feature, which usually goes together with this kind of duality. That is, that what is viewed as an elementary particle in one description gets mapped to what is viewed as a composite particle in the dual description. This has been called particle democracy by Ashoke-san in analogy with the nuclear democracy of the Geoffrey Chew program in the 60s. I don't know if you are familiar with that, but it's the bootstrap programming. But so this is just to explain the origin of this label. Okay, so this is still in general terms a more detailed characterization of Weakstrong duality. Now we'll see that more precisely by focusing on the origin of this notion of Weakstrong duality and what it gave rise, that is electromagnetic duality and its generalization to quantum field theory and string theory. The history of this idea can be seen as a successive progressive generalization starting from Dirac's theory of magnetic pole. We are in the first half of the 19th century, just to give you an idea of the development, to the dualities of quantum field theory. From Dirac's theory to the dualities of quantum field theories, and the seminal result is the Monton and Olive conjecture in 1977, and the generalization to supersymmetric field theories. And here I have listed some of the people who contributed in a seminal way to this generalization. To arrive to the so-called S-dualities, this is the way in which they are named in the context of string theory. And perhaps you have heard about the fact that the 5 types of superstring theories in the mid-90s were understood as the dual of the same theory, M theory, mystery theory, matrix theory. So just to give you an idea of the development of this idea and where it has led. So today I will stay here more or less at this point of the history. The Monton and Olive duality, conjecture duality. And since I'm speaking about this conjecture, I'm quoting from David Olive, who has written a lot about Weakstrong dualities. He was really one of the main persons in the field. And this is a quote taken from a book he published with Philip West in '99 on the duality and supersymmetric field theories. And supersymmetry, I don't remember now the exact, but it's in the reference title. So let's write this quote. Electromagnetic duality is an idea with a long pedigree that addresses a number of old questions in theoretical physics. For example, why does spacetime possess 4 dimensions? Why is electric charge quantized? What is the origin of mass? What is the internal structure of the elementary particles? How are quarks confined? As you see, quite fundamental issues. And it's true that this kind of duality, in a way, is connected to all these issues and it also provides some answers. How? And to understand how, one can follow the main developments of this idea. And it comes out. So I'm not doing that here, but just to give you an idea. So let's start very, very quickly from Dirac's theory, just to situate the origin. You all know free Maxwell equations, and here the duality is very clear. If you exchange electric and magnetic field, the equations are invariant, and the duality is a symmetry of the theory. Dualities are not always symmetries in this sense, that the equation of the theory are invariant. But in that case, we say that it's a self-duality and it's a symmetry in the standard meaning, according to the standard meaning of symmetry. So what happens? This is free Maxwell theory. Of course, if you add electric sources, this manifest symmetry is broken, but you can restore the symmetry by adding magnetic sources. And then the duality is more general, involving also magnetic and electric sources. And again, you have a symmetry of the theory. This is in the classical setting. Now, going to the quantum setting, there were some problems. And Dirac's theory of magnetic poles was a theory to provide answers to these 3 points. It was the first first theory formulated to provide an answer to this point, that is to find a consistent generalization of electromagnetic duality to the quantum context. Why consistent? Because you will know that if you have magnetic source, you have a problem with the vector potential, with introducing the vector potential. The vector potential is essential for the coupling of electromagnetism to quantum theory, so by means of the minimal coupling and so on. I think I can take this for granted, or okay, we'll see. We can, in case after doing some, but to obtain to generalize the electromagnetic duality to the quantum context. The vector potential is the essential tool, and when you add magnetic sources, you can introduce it with the divergence of magnetic field equal 0, which is the standard way for introducing, because the divergence of B will depend on the magnetic source. It's no more 0. So then there was a problem already for the classical theory, that is magnetic sources.
No, can I actually see? Just have we have the slides.
They can't hear?
I can hear you.
They can't see.
They can see?
Okay.
Okay. But the slides are enough.
Fine.
Now they should see you, right?
Perfect.
Okay.
Thanks.
Thank you for telling us. Thank you.
Okay. So isolated magnetic charges were not observed and are still not observed. So the whole discussion must take acknowledgement of this fact that monopoles have not been observed still. The theory is 100 years old, almost, but they have not still been observed. And it provided, this theory provided also reason for charge quantization. So these three things motivated Dirac's theory of magnetic poles. Let me just give you an idea. Dirac achieved to prove that it was possible for a magnetic charge to occur in the presence of an electric charge without disturbing the consistency of the coupling of electromagnetism to quantum mechanics if the following condition was satisfied. And you see, it's an inverse relation between the two coupling, between the electric charge and magnetic charge, which is known as the Dirac's quantization condition. So this condition, combined with the duality correspondence between the couplings, leads to the following inverse relations, which, in a sense, is the origin of the Weakstrong duality we speaks about. Even if in this setting it has not the meaning that it will have later. If the charge is small, you see here, weak coupling, the dual charge is strong, so strong coupling, and vice versa. So this was the starting point for the development leading to the Weakstrong duality of field and string theory. The inverse relation is the way to explain why one couldn't see the magnetic charge, because the coupling was so strong that isolated charge could not be seen. No? This was the way for explaining it. And the quantization of electric charge follows naturally if you have a magnetic charge, because the electric charge comes in integer unit of the magnetic charge. Is it okay? Clear? So for Dirac, this was really a big motivation for going on in this direction. One of the main motivations of his theory of magnetic monopoles. So this is what I had just said. So how was it generalized? What does this mean? This happened in the 60s. Early 60s, the first generalization. So after some years, a number of years, the next significant stage was the seminal contribution by Skr in '61. Then the conjecture of Skr was demonstrated by Coleman and Mandelstam 15 years later, something like 15 years later, and the Monton and Olive duality conjecture. So these are the results I'm speaking about today in some more detail. Note that these developments were deeply intertwined with other contemporary threads in fundamental physics. Just to give you the whole panorama, that is the development of the theory of solitone in the context of quantum field theory, the development of supersymmetry, the theoretical activity toward unification of all fundamental physical forces, the so-called grand unification theories, and string theory reinterpreted in the 70s as a theory of all interaction, including gravity. So this is the panorama. In a sense, this idea of duality, Weakstrong duality, connects all this kind of development. together. So it has remarkable implication if you situated it in its context. So let me start with the first case of Weakstrong duality in quantum field theory, which is the Signboard-Turing duality, so-called. It's a duality relating on the one side, the so-called Signboard model, which is a theory describing a massless scalar field, bosonic field on the one side, in one space and one time dimension. So here, this duality is in 2 dimensions, 2 space-time dimensions. It's linking, relating theories in 2 space-time dimensions. So on the one side, we have a bosonic field with interaction density proportional to a cosinus. So here the name sine comes from the sinus in the equation. And on the other side, we have a fermionic field, a massive fermionic field with a self-interaction. So you see, the connection is between a massless scalar field, bosonic field, and fermionic massive field. The one is free, the other is with a self-interaction. The one has this kind of interaction, and the other is with a self-interaction. So quite different theories with different Lagrangians. Here, the theories which are correlated are really different, apparently. So this duality, a dual equivalence between these 2 theories, implies in particular that there is a precise correspondence between the soliton states here, the theory of solitons that I mentioned before, the soliton states of the quantized Signboard theory, and the elementary particle states of the dual massive theory model. And this equivalence is a weak-strong duality in the sense that the weak coupling of the Signboard fields correspond to the strong coupling of the massive theory model. We'll see this in some more detail. So this is just a general description. So I have mentioned solitons, so let me say just something about this notion, just to understand what is going on. So solitons are defined, characterized as extended solution of classical nonlinear field equations. And they were so called by Zabusky and Kruskal, I think one pronounced their name in this way, in 1965, to indicate humps of energy propagating and interacting without distortion. So the idea was introduced in the first half of the 19th century to describe solitary water waves which propagated without deformation. And then it was taken again in the context of quantum field theory in these years. And the pioneering idea of Skern was the following one, that a soliton could be interpreted as a quantum particle in the complete quantum theory, and that a dual correspondence could be established between this sort of particle and the familiar elementary particle of quantum field theory. If you think about it, a soliton as a hump of a localized energy, although finite extended, can be assimilated to a particle because it doesn't deform, it's just stay. So it was natural to analyze if there were a possible correspondence, if this soliton could be interpreted as a sort of particle. And this is what was done in this context by Skern first, and then by others. So how one could see this analogy, this connection between soliton and particles? This could be shown by constructing a new field operator of which soliton states were the quantum excitation. So this was a result conjectured by Skern and later proved precisely by Coleman and Mandelstam. In this sense, so the Signboard quantum soliton was proved to be a particle, and this particle was the fundamental fermion of the massive Turing model. In the usual sense that the concept has in particle physics, that is, as a quantization of the wave-like excitation of the field, is the sense of the particle in quantum field theory. So this means that in the full quantum theory, particle could appear as solitons or as quantum excitation, depending on the way the theory was formulated. So the status was equivalent. In this sense, we speak about particle democracy. Let me go on, it will become more clear, I hope, what I'm saying here. So historically, this was the first explicit example of a dual interchange of neutral charge, that is the particle in the usual sense in elementary particle physics, and topological charges in quantum field theory, where neutral charges are this quantum number characterizing the familiar elementary particles of quantum field theory that are associated by means of the famous neutral theorem with the manifest symmetries of the theory, and they depend on the symmetries of the dynamical equation. While the topological charges, which are quantum numbers characterizing the soliton states, are quite different in origin. They don't depend on the dynamics, but they are conserved quantities, just as the neutral charges, and though they are related to other characteristics, that is to the soliton solution behavior at spatial infinity. So these are topological properties. It's another origin with respect to, but they characterize the soliton solution, the soliton state. So we have these two kinds of quantum number characterize the different way of appearing of particles in this context. So what was the Montano-Olive duality conjecture? It was the extension of these ideas to the more realistic case of four space-time dimension, because one space dimension and one time dimension was at the time not considered very realistic. Although today it's no more so, but Montano and Olive wanted to generalize this duality to the realistic case of field theory with three spatial dimensions and one time dimension. So their conjecture was on electromagnetic duality in a specific case of non-abelian gauge theory, that is the interesting theory from the viewpoint of particle physics. And what they conjectured was that there should be two dual equivalent field formulations of the same theory, in which electric or neutral charge and magnetic or topological charge exchange roles. So here, to understand this conjecture and how it could be made, we must consider a seminal development in this history, which was the interpretation of monopoles as topological solitons in the context of spontaneously broken field theory. Excuse me, I'm introducing a lot of things, but this is the, otherwise I could not be precise in what I say. And this was a result obtained by Toft and independently by Toft and Polyakov. So they are called Toft-Polyakov monopoles, this kind of monopoles. So you see, another idea comes together in common, that is spontaneous breaking of symmetry. So, what was this duality? It was a conjecture that a dual version of the Yang-Mills theory with quantum field operator that we could have a dual version, of the Yang-Mills theory with quantum field operators creating magnetic monopoles, the topological solitons, rather than the original DH particle, the electrically charged particles. This is the dual. So you see, the roles are reversed in this dual description. So a perfect duality in the treatment of electric and magnetic charges was therefore suggested, which is really a generalization of Dirac's electromagnetic duality to its quantum field theoretical form. Now, let me say that this was still a conjecture at the time of the paper. It was really proved only later by extending it to a supersymmetric field theory. So at this stage, it was still a conjecture, but they had good evidence for it. So note that also in this case, the duality is a self-duality. So the dual description is formally the same as the original one. The Lagrangian is the same one. This is different from the case of Signboard and Tirinuk. So how to understand this case? You remember I told you just at the beginning when I introduced the general characterization of Weakstrong duality that we have a case of the same quantum theory, if you want, with different classical limits. So now we can understand this a bit more in this sense that consider a quantum field theory containing particles carrying electric charge as well as particles carrying magnetic charge. So understand this magnetic and electric in a generalized sense. It's not the real electric and magnetic in the sense of electromagnetism. It's a generalized sense of electric and magnetic. One can have two possible classical limits depending on which charge is kept fixed in the limit, while taking the classical limit with h bar going to 0. So if you keep the magnetic charge fixed and you consider the limit of small electric coupling corresponding to the classical limit, then the magnetically charged particle have the role of soliton, and the electrical charged particle have the role of elementary particles in the classical limits. And then you quantize starting from this classical limit. If you keep the electric charge fixed and you consider the limit of the weak limit for magnetically charged particle, then the reverse happens. The electrically charged particle arises as solitons, and the magnetically charged particle arises as elementary particles. So you have two different possibilities for the classical limits, and you quantize, you have two ways of quantizing, according to from which classical limit you start with. And then you arrive at the same quantum theory, or at two quantum theories, which are completely equivalent. So this is the way of understanding this kind of duality. So if you remember, this is a slide we have already seen, the general characterization of Weakstrong duality. Now you can understand a bit better what these apparently different mean. And when what is this correspondence between elementary and composite is the correspondence between electric charges, neutral charge, and topological charge, solitonic states. So this is the way of seeing it. So this terminology, elementary and composite, is a bit misleading because it leads you to think of composite as composite in the neurological sense. It's a bit different. It's not a composition in this sense. You have solitons, which are extended solutions, but not necessarily they are composed of the other particles. So it's better to speak about neutral charge and topological charge, which is less confusing, perhaps. So, just going philosophically on the interpretation of this dual pairing. So the duality regards the different modes of appearance of the particle when considering the different classical limits of the quantum theory. There are dual perspectives, if you want. So the democracy associated with the duality is linked to this kind of modality in their appearance. In this sense, it's more a representational, functional democracy rather than an ontological one. It's the mode of appearance which is implied here. Okay? For this kind of duality. And this is in accordance with saying that the physics remain the same, because they appear differently, but the physics remain the same. And that what changes is just the way of looking at it. We have different perspectives. Clarifying the nature of the complete quantum theory. So we don't really have an issue of underdetermination here, as it is sometimes supposed. How much time do I have?
About 10 minutes or so, maybe?
10 minutes?
Yeah,
Okay.
okay.
It's okay. Yes. Okay, let's go back to emergence. So all we have said is just to clear in which way duality leads to emergent feature, novel feature. Both the case studies we have considered, gauge gravity duality and generalized electromagnetic duality. We can notice similarities between the two notions. We have novelty, because one theoretical description contains novel aspects, if you want, with respect to the other. Robustness, okay, let me skip over robustness, because I think it needs more elaboration. We have scale difference, which is a typical feature when speaking about emergence. In this case, it's the difference between weak coupling and strong coupling regime. And we have limits, but limits in a different way with respect to the limiting relation between theories we are used to. But we have limits. The classical limits, we shall do them. So these can be the similarities, coarse-graining similarities, if you want. But we have a contrast, that duality is a symmetrical relation. We have mutual novelty between these. While emergence apparently is not a symmetrical relation. So just let us give a closer look to the Signboard and tree model, just to understand better this mutual novelty feature. So, as said, it's a dual equivalence between a theory describing a massless scalar field with interaction with potential proportional to the cosinus. Beta is a real parameter here, and we can show that it plays the role of a coupling constant. And the massive Turing model, which is a theory of a massive self-coupled fermion fields. The interaction is of this form, where G is the coupling constant. So I'm going just in a bit more detail than before. Let's say this duality was first conjectured by Skirm and then confirmed by Coleman and Mandelstam. So what was Coleman's starting point? He was able to establish a precise relation between the parameter beta of the Sine-Gordon model and the coupling constant of the Turing model. In this way, the two parameters were thus related. So it's an inverse relation, as you can see. So the Weakstrong derives from the inverse relation. It's a Weakstrong duality because if you take the weak coupling of the Sine-Gordon field, this one, what did I do? Sorry. I wanted to push this here. The red, but I don't see. Okay, so this is the weak coupling. It corresponds to the strong coupling of massive model, okay? And note that the relevant parameter is this one. So the weak coupling corresponds to the classical limit H. They goes together. So if you take this relation between the parameters and establish an appropriate dictionary between the dual quantities, which is this one, you see here you have the fermionic field and here the bosonic one. And you have this relation between these quantities, the dictionary about which Sebastian spoke in his talk. Then one can demonstrate the duality by comparing the two perturbation series for both theories. And you can just identify the amplitudes in this series when you do the precise appropriate translation between them. So this is just to give you a better, more precise idea of what this duality consists of. So it doesn't, otherwise it's still a bit like something you must just believe. Let us so compare duality and emergence in this specific case. What happens? If you start with a massless bosonic field, the duality leads to the emergence, if you want, of massive fermions, a massive fermionic field, with this kind of interaction, and vice versa. The vice versa is known as bosonization in the literature, and it's used in condensed matter physics, for example, something well known. So, through the duality, we have a two-sided process. On the one side, you make fermions out of boson. On the other side, you make bosons out of fermions. This is more familiar to make bosons out of fermions. If you take two fermions and the Bose-Einstein condensation is very familiar. This is another mechanism, but it's a familiar notion. Making fermions out of boson is less familiar. This is more strange. But it's a two-sided process, you see? And the duality defines the precise modality in which this emergence obtains. They are intertwined. Conclusion, what do we have here? A two-sided emergence. So, at the beginning, I didn't put a question mark, but just an exclamation point. But perhaps better to be more prudent. A little bit. So, I think that comparing duality with the notion of emergence can throw new light on the notion of emergence. So, we should probably, it can suggest possible enlargement of the notion. Because it's true that we have novelty here. We have novelty, but a two-sided novelty. References. I have put 3 of the classic references. There are many more, of course, but these are the historical paper, the first 2. And this is the text, the book volume I was referring to by Olive and Philip West, Duality and Supersymmetric Theories, which is really a beautiful collected volume for this history. And all of this can be found also in some of the paper appearing, we hope, in a special issue of the studies. All the papers are in. Most of them are already open access online. It's a special issue on dualities in physics. With Dean Rickless, we are guest editors of this special issue. And here I have just put the paper speaking about this Weakstrong duality in a more precise sense, and the paper by Sebastian on duality and emergent reality, which is the basis, and one of the papers he has written on this topic. And the last one is a beautiful paper by Joe Polshinsky, which is one of the leading string theorists, on dualities of fields and strings, where you can find much more. I spoke about just a very teeny bit of what he's describing in this paper. Okay, this is all. Thank you.
Okay, as we prepare.
So it's a question about emergence and topology. But you suggest that emergence is symmetric. Right? If you have 2 dual series x and y, y is the measurement with respect to x, and x is the measurement with respect to y.
In a sense,
It's a relation that's quite different from the notion we usually use as
yes.
measures. So I was asking myself whether would it not be better to for instance, if we have ontological dependence, which is symmetric. We can say that one is the other, it's going both ways. So I'm not
structural notion.
So your emergence is not.
It's not necessarily ontological.
Define emergence between theories, practice a common use in philosophy physics. This is not the way in which it is used outside of philosophy. It's not a relation between, it can be a relation between systems, not between theories, whereas dualities can be a relation between theories. So, I mean, a terminological point, perhaps you should use a neutral term like interpretability, interpretative, or something which is more a relation between theories, and not emergence relation between systems, physical systems.
You can choose the items you want to read. So you can speak about theories, you can speak about systems, you can speak about properties, about phenomena. When you have an equivalence between two theoretical descriptions, then you have dual correspondence in properties. So it depends. I don't think that the terminological person can say much in this context. I don't think it changes much. I don't think. But thank you for saying now one can be more precise. In fact, I don't think it's changed much. You can just focus on the system, you can focus on the theoretical description of the system.
So there's no questions in Chicago.
Yeah, hi. Thanks for the talk. I think that one thing that I find important to clarify this situation is the quantum to classical distinction. And some of these questions about emergence from one to the other is and kind of phrasing that as in the way that one might be tempted to do might be because one is kind of looking at the classical picture too seriously, in the sense that it is kind of a stepping stone to get to the quantum description, and that at that level you see the equivalence in terms of correlation functions and all that. But then, of course, one is still interested in getting back to classical descriptions in certain limits. So the situation, as far as I understand it, is rather that you have two classical starting points that are kind of used to describe the quantum picture, and then you have that as the real starting point, and then in certain limits of that quantum picture, these different original classical descriptions can appear. So in that sense, it's kind of this two-sided, or if there are kind of even more dual pictures, different kind of behavior emerging from this kind of underlying quantum picture at different limits. So I think this way of that's kind of how I think of it, and I think that is consistent with what you're saying. But there was one thing that I was kind of worried a little bit about. It was kind of using the expression perspectival when talking about those limits, because taking a specific limit should correspond to limiting to a specific physical situation, I think. So they shouldn't be kind of an optional choice in that sense. It's rather that in where the big quantum theory that kind of can model a lot of different physical situation, different kind of effective classical behavior kind of appear in different limits. Do you agree with that picture?
Yes. Let me just say something that what you are describing, and I completely agree with you, is the situation when we have quantum theory and the different classical limits. Take the case, this is also the reason why I have even more detail on it, the case of Signboard and Turing. Here you have two different quantum theories. So you have two different perspectives on the same physics.
Okay.
So this was a sense image.
So that is a slightly different situation compared to that.
It's a bit different situation. This is the reason why I have taken this example to compare Twilight and Imagines. emergence.
Okay.
Because the motononolic, the self-duality is not so effective in this sense. This is not a self-duality. Because the theories are different, they have different Lagrangian, but you can establish this dual correspondence.
But couldn't one still ask those questions about if it is a real duality and it's not just used as a calculational tool, and one thinks that the quantum description completely exhausts the situation, couldn't one still kind of ask this question, given a specific situation, which is described by two different kind of purely theoretical ways of describing that, one can still kind of ask the question, what does that look like? It's kind of like asking the question pairwise for each kind of model. You're thinking of the theories, which I think is like the semantic view of theories, which is useful, having like a theory is a collection of models, and then another collection of models, and once you dual pick them, like one from each that are corresponding to each other, then if they describe the same physical situation, there should be kind of a unique answer to what kind of the phenomenal or effective or physical picture would be in that situation.
Yes.
Okay, good.
I think it's part in this direction. It's part. Yes. Nick?
So can I follow that up a bit? I mean, so when you look at Sen's definition, it seems like there's no way that could possibly make any sense in a certain way, because, you know, we've got this more fundamental theory. There's just one, according to the duality at the fundamental level, there's just one fundamental theory which we can dress up in two different ways. But if it's really the same theory, it has to be able to explain all the same things. And so if one of the duals can explain a particular classical limit, the other dual can. Otherwise, they're not the same. They have different, they just have sort of different predictions. So it seems to me, the resolution must be, even at the classical level, it sort of turns out that the things that you thought classically were really distinguishing these theories, given the fundamental theory, really can't be real differences. I mean, they're just in your sort of classical models. So if you actually went through and looked at the fundamental theory and thought about how you could sort of operationalize the observables and the classical observables, it would still sort of turn out that these two classical theories have to be empirically equivalent. I mean, the duals are empirically equivalent.
Given a fixed
classical
model, yes.
Theories.
Given a fixed pair of models.
Yeah. Yes.
But then it could be that kind of effective picture can be different for different kind of when you tweak that. So in that sense, it's
I mean, but so any sort of sector that one dual can explain, the other dual must be able to explain by the duality.
Yeah, in principle.
Right, even if one of those sectors looks more like one of the duals than the other, as sort of you're saying. So any sort of difference between the classical theories can't be an empirical difference. They have to be empirically equivalent by the fundamental duality. And what we've learned something about what the real empirical content of those classical limits is by this duality as well. Does something like that sound reasonable?
Yes, I agree.
I have a follow-up. You spoke at some point of confirming that first conjecture. Then I started to ask myself, okay, what does it mean to confirm a duality in first conjecture? It could mean a number of different things. It could be that you suspect there's a theoretical equivalence between two descriptions of theories, and then you prove, by some sort of mathematical proof, that there is such equivalence.
You compare the interpretations. Turn by the method. If they are identical, then you prove the equivalence.
Okay.
In this sense, the symmetry helps because it's simplified in the situation.
What you compare to?
Yes.
So you thereby
The proof was like perturbative, I think.
Yeah.
It's theoretical work to establish equivalence between
Yes.
two descriptions.
So this is also the sense in which string theory says they have proven duality.
There's really two aspects of duality. On one hand, you have to have an equivalence of physics. On the other hand, you have to have some notion of distinctness. There have to be two numerically distinct things which are dual. Dualism.
When you have self-duality, you have different regions around the space of the same thing. When you have
some difference.
Yes,
one
you have
kind
some
or another.
difference. Yes.
That you then compare.
Yes.
And you discover that they do indeed give you the equivalent physics.
Yes.
The equivalent physics. And one way I thought this could be done, what makes sense, maybe to believe that this kind of also would be the right way to think about it, is that you have, in particular case of the self-dualities, monotone dualities, you have self-duality, really the way maybe two perspectives of the same theory that gives you the same physics in a way. How could there be anything distinct that's dual to one another? And you say you can distinguish these two things by having different classical elements. And one thing to confirm that would be to show that where the equivalence is kind of obvious or free or maybe done by self-duality work, you have distinct classical theories which are somehow giving you distinct physics at that level that may nevertheless both be valuable, acceptable classical theories in some way of passing as physically okay kind of classical theories.
I wouldn't look at these classical limits as distinct from the quantum theory. That is, you must look at them as the starting point for quantizing and looking at quantum theory. So when you are looking at the experimental side of it, you should have the complete theory.
So is it then sort of in the context of discovery that people did in fact start out from distinct classical theories, which they then quantized and they discovered in two cases that, we actually know this.
It was his model the way it was discussed. But in the case of Signboard theory, so the starting point was Kern. As Kern was searching, we were at the beginning of the 60s, so the standard model was not there, it was before, and there is approach, the semantics approach was starting, and so on. And it was difficult to treat quantum field theory with strong coupling in the derivative terms. So when I was searching for other kind of theories, and he looked at I don't remember now exactly, I can give you the details, but the problem was to introduce a fermionic field in the context of a bosonic theory, and he found his way of introducing it. So it was not just starting from classical theories and then exploring, it was quite a long process. And then Coleman and Mandelstam just generalized it and proved it. But in the quantum theories, it's not a classical. They started from the quantum theories. Okay.
That's very helpful. Do you have more questions in Chicago?
There's a question from YouTube,
Okay, let's go for it.
and it's from Johan. So he was restricted to 200 characters, so I don't know. So there may be a little interpreting of his question. So what he says is, can we infer that a duality between the Turing and Sine-Gordon models can provide explanations for unknown or less known properties of composed particles. So to interpolate my kind of editorial here, and sorry, Johan, if I got this wrong. It's sort of an interesting kind of. I think the question is about another sort of symmetry versus asymmetry here. You might think the duality is a sort of symmetrical relation between the two of them, but you might think the explanation relation is usually asymmetric. So I guess, does the scalar field explain the fermions and the fermions explain the bosons somehow? I think this, I think it's taking the question in another sort of direction, but is there another kind of issue like that going on?
Yes. This is what.
Would you care to elaborate? You can use 200 characters too in your answer.
Yeah, I have a question which is similar. You said that the dualities, some of the dualities described are reduced by some mapping between the inverse spaces of these. And you also said the thesis is that these form of dualities, the relation of duality is it's double emergence. And I want to understand this thing. Whether you can say this, the question was whether if you take a standard case of emergence, whatever it is, something was emergence, you can recast it. So if one theory describes something which is emergent, or the other theory describes, you can recast it the same way, also sort of the same sort of mapping function from one, or the state space of one to the other.
Sorry, I did not still understand your question, or which is the question exactly?
The question is, when you have, that's fine, I'm sure it was a definition of duality. In some cases, duality is induced by sort of a mapping state space of the keys.
So that's right, yes. The evidence, the isomorphism.
Exactly. The other state space. The question was, take a case of emergence, something which could be called emergence, whatever that is. Could it be the interrogation of emergence, or at least there would be emergence in the physical truth? Could you recast is there a relation which is similar to that in the case of quantities, so some kind of injection, isomorphism between the state spaces?
Dimensions?
Yes.
Your question is if one can define emergences in isomorphism, and doesn't use?
Well, because
I wouldn't try to characterize emergence in this way. I think the similarity is more a loose one,
more superficial.
More superficial, but
you're reminded of emergence because there's novelty.
There are not intertranslatable.
There's not really a key point.
But in a sense, the duality guides the way we have emergence. It's more in this sense they are connected.
Yeah,
I would say
the claims that there is emergence.
The fact that you have emergence on
both sides.
On both sides.
There's a relation between the thing and emergence. It's not the same force between.
No, but the emergence is not from the classical. So perhaps I feel that this is a bit confusing. The emergence, the novelty, is between the two quantum theories.
Yes.
Not from the classical.
Okay, exactly. But the relation between
So on the one side you have boson, okay, on the other side you have. So if you start from here, the duality takes you to the description way further.
Exactly. This does not seem to be the same relation that forms the dividing application of emergence. Would you say also that the classical theory emerges, classical theory emerges from the quantum theory in some new case from The question is there really a deep similarity between cases of what is called emergence and what beyond some superficial, what is novelty if you change from one perspective to the other. But the same phenomenon.
I don't think it's exactly the same, despite interchange between one and the other. It's just they are strictly interconnected. That not describe emergence as an atom of the same. It's difficult also to go into details.
Yeah. Sure. I'm not
Sorry,
competent to discuss.
that's not clear enough.
Also, the thing is both the duality foresight emergence. Yeah, I mean, if you want, since we are not defining emergence, it doesn't seem to be this deep identity that goes on in cases of emergence.
There's a question, Chicago.
Yeah, I think I kind of, I didn't quite pick up all of that exchange. I didn't quite hear all of the question, but I think it was referring towards the end of the talk where there was a slide comparing emergence and duality. And it just sort of, maybe you were saying it then and it just somehow didn't sink in, but now it's kind of clicking, going back to the Butterfield slide at the beginning. I mean, is part of your point here, and I'm sorry if this was like the point and I'm kind of just being really slow this morning. I mean, when you look at Butterfield's definition, it turns out because being composite is one of the ways you can have emergence, he hasn't actually defined an asymmetrical relation. You've given us examples where, right, it turns out that emergence is symmetrical because each side is composite of the others. Is that kind of part of the big payoff here? And I guess I do feel a little slow now, having kind of just sort of realized that. Yeah?
I can only agree with you.
Yeah, okay, that's pretty neat.
No, it's very neat. Since this is a work in progress, so I'm just very happy if you have suggestions.
Then maybe I connect into that. So the idea is to insist on calling it emergence, because you might just say, well, forget to talk about the emergence. Let's just talk about the dualities, what goes on with dualities. There's novelty, symmetric novelty, what's happening, you just analyze that without bringing in the notion of the concept of emergence. That might be one option. But that given the very last reactions we had to make, this point is that's very helpful. So the reason why you want emergence, talk of emergence is because it is a case of elementary to composite sort of relation, which is usually cast as or understood as a form of emergence.
Yes, it resonates. It's not a composite in that precise sense. But there are very close analogies because it's true that in Gaussian organization you have emergence, if you want, of other objects. So it's similar, but it's not exactly the same. So this is the reason why I was motivating in speaking about emergence. Because, is it okay? You agree? But it may be that it's a red herring and we shouldn't speak about emergence. But there are so many features which are similar. So we can also reason in this way, say, look, there are all these features that are similar. So when you speak about emergence, be careful that this is not enough to characterize emergence. Yeah?
I mean, you can see someone trying to use this, writing a paper where this is a counterexample to Jeremy's account, right? I mean, he can't be wrong about he can't be right about emergence because here's a case where it turns out to be symmetrical, but we all know emergence is asymmetric.
Can I ask a question? I mean, bearing all this in mind, I'm intrigued by your claim that there isn't a problem of underdetermination, because it seems that we do have two incompatible descriptions, one where emergence is going, you know, up, one where emergence is going down, and unless we can display something that's consistent, we are faced with the problem of underdetermination. What's the sound?
They turn the sound off too.
Yes, I think you
Thanks.
have underdetermination when you have two different descriptions excluding, mutually excluding one. That is, you don't have, if you see this different description as a perspective on the theory, giving you different aspects of the same theory, then it's not a case of underdetermination. Are you agreed?
Well, I don't know. I mean, I'm thinking here of cases like in, say, 1926, you've got wave mechanics and matrix mechanics. It seems like there you've got two incompatible descriptions, and what convinced us that they were not incompatible was the production of a context in which we could show them to be equivalent, namely Hilbert space. So I don't feel like we've got that context in which they've been shown to be equivalent. We've just got these pairing offs of perturbative expansions.
So I'm not sure I have understood you correctly, but so this is not a case of underdetermination. Are we agreed that the wave part, the wave?
Well, it may be, it may not, but I feel like we need to show a unified framework for it to be not a case of underdetermination.
No, but this is what happened to Olive theory.
That's what you're
for
supposed to be
example.
showing with
It's a unified framework,
perturbative equivalence.
different perspective. I don't know. You
Okay,
can-
maybe I'm missing something.
So, any last question? Well, if not, please join me in thanking